Okay, so how do we know if evolution has taken place at all? If a population has changed over time, which is the definition of evolution? Well, Hardy-Weinberg is a model that we can use to compare against. Okay, so we think of it kind of like a control in an experiment. So let's talk about what is Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium is going to describe populations that are not evolving. This way, if we calculate what Hardy-Weinberg should be, and the population is significantly different from that, we can say that that population is evolving. So it is a model, okay? Here are the qualifications. Okay, genotypic frequencies, that means the frequency of alleles in a population will stay the same if 5 conditions are met. A very large population, so small populations change rapidly, so the larger the population, the better. No immigration, that means moving out of a population, or no immigration, which is moving in, which means there's no gene flow. So if you have a large population, you'll have no genetic drift, because genetic drift tends to affect only small populations. If you have no animals moving in or out, then you will have no gene flow. You'll have no flowing of genes into the population. No mutations. So no mutations happen that create a phenotypic consequence, right? So no new alleles are added to the gene pool. Random mating, so we don't have any sexual selection. So there's no birds doing with their fancy plumes or doing the dances or anything like that. Females and males mate at random. And no natural selection. So all traits that they have, there's no survival of the fittest. Everybody is equally fit for the environment. So there's no one adaptation that's more fit than another. We use it as a model to compare. So predicted genotypic frequencies are compared with actual frequencies. So Hardy-Weinberg is a prediction if no evolution is occurring. So let's figure out how to calculate if no evolution is occurring first. Okay, it is used specifically for dominant and recessive genes. So if it's like co-dominant or something like that, it makes things a little bit more difficult, and the math is difficult, and it's not exactly Hardy-Weinberg, okay? Now, so you have to know the frequency of the recessive homozygotes. So if an animal, remember this from our dominant recessive traits. If you have the recessive trait, let's say blue eyes is the recessive trait, you have to have both recessive alleles. That allows us to be able to calculate everything else, okay? So Hardy-Weinberg is based on simple Mendelian genetics, that Punnett square that we did, okay? P squared, this is the number of homozygous dominant plus 2 times the number of heterozygotes plus the number of homozygous recessive squared should equal 1. Okay, so P equals the frequency of the dominant allele, Q is the frequency of the recessive allele. P squared is the frequency of homozygous dominant, 2PQ is the frequency of heterozygotes, and Q squared is the frequency of homozygous recessive. So we can get every other piece of this puzzle right here if we know the number of these, we can move forward and figure the rest of it out. All right, so now let's try these. All right, here are our dragons over here on the left. Remember, P is the frequency of the dominant allele, and P squared is the percentage of homozygous dominant. Q is a recessive allele. Q squared is the percentage of homozygous recessive. 2PQ is your heterozygous individuals. All right, so now we are looking at the wings. All right, so wings is dominant. Wings is dominant. So how many not wings do we have? So we have 6 that are homozygous recessive. 6 of them. Now, how many do we have total? 21. So the percentage is 6 out of 21, 0.28. Okay, so that 0.28 is our Q squared. Now, if we want to know what Q is, we have to then get the square root, because the square root is the opposite of being squared, right? So this is homozygous recessive individuals, which means they have, let's say it's W, 2 little w's, okay? We want to know the frequency of just one little w, so we 0.53. Oh, 0.53. All right, now P plus Q equals 1. So if 0.53 plus, we don't know, P equals 1, then if you take algebra, you know that P equals 1 minus 0.53, which is, for P, 0.47. All right, now we just have to get the square root, or we have to square 0.47. So we have to take 0.47 and we need the square root. There we go. I mean the squaring. We need to square it. So that is P squared is 0.22. Now it's just a math problem. So we take P squared. So here's our formula now. Hold on, let me eliminate that. Here's the formula we're going to use now. All right, so P squared is 0.22 plus 2P, which we know is 0.47, Q, which we know is 0.53, excuse me, plus Q squared, which is 0.53. Nope, 0.28, duh. All right, this should, when added up, equal 1, okay? But first, we need to use the calculator and calculate 2PQ. So 0.49, okay? Now, so this is right here, 0.49. So let's do the math and see if we get 1 plus 0.22 equals plus 0.28 equals pretty much 1. If you round up, that's 1. So we got all of our frequencies exactly correct. I actually want to start with number 2 over here. You have a sample population in which you know the percentage of homozygous recessive, okay, so Q squared right here equals 36%, okay, or 0.36. Okay? Now, if that's Q squared, we need to get Q. How can we get Q? Square root of Q. So we need to take Q equals Q squared, the square root of Q squared. Okay? That's the definition of Q, basically. 0.6. Okay? Now, that is, so now we have, let me change. Now we have Q squared, and now we have Q. All right? Now let's remember P plus Q equals 1. So if Q is 0.6, then what is P? P equals 1 minus 0.6, which is 4. Okay? So, oh, I'm sorry, 0.4, duh. All right, so now we have P, we have Q squared. Okay? So the frequency of the genotype 2A, which is Q squared, is 0.36, which we got from right here. The frequency of the A allele the little a, we got from right here. The frequency from the big A allele, we got from right here. So 0.4. All right? The frequency of big A is, if we have P, then we just need to square 0.4. So let's get out our calculator again. So 0.16. So this is your big A, 0.16. All right? Now, let's just do, remember our equilibrium, P squared plus 2PQ plus Q squared equals 1. Okay? Now we need to know big A, little a. Now we need to know big A, little a. So how do we do that? Big A, little a is 2P, which is 0.4, Q times 0.6. All right? Now, how do we know if we're right? Let's plug it in. So we said P squared was 0.16. 2PQ is 0.48. And Q squared is 0.36. Now, if I get out my trusty calculator, 1. Exactly perfect. Okay? So again, start with your Q squared, which is what they gave you, and work your way back. Now, let's talk about the brown rabbits. So, population of rabbits may be brown, which is dominant, or white, which is recessive. Brown rabbits have a homozygous dominant or heterozygous, and white rabbits have the genotype little b, little b. Now, this time, they're giving you P squared. They're giving you the frequency of the homozygous dominant. So this time they gave you P squared equals 0.35. We do the exact same thing. Pretend it's Q if you want to. How do we get P squared? How do we get P? P is P squared, the square root of. So we just discovered P squared is 0.35. 0.35, and we take that square root. Boom. Oh, what was it? Sorry. 0.59. All right, so now we have P, and then we're going to do the next step, which is P plus Q equals 1. We have P, which is right here, 0.59 plus Q equals 1. So Q equals 1 minus 0.59. Q equals 0.41. All right, so now we have P squared, we have P, we have Q, and now we just need Q squared. So Q, let's do a different color. So Q squared is going to be Q squared, 0.41 squared. So we just get our little calculator back out. 0.41 squared is 0.17. Okay, so this equals 0.17. That's Q squared. Okay, now, all right, what is the frequency? And then now we need 2PQ. So 2 times 0.17 times 0.59. 0.20. All right. Now, the frequency of heterozygotes, this is your heterozygote. So your frequency is 0.20. The frequency of the big B allele, so this is P, not P squared, P. So P is your big B allele. Your frequency of P is 0.59. Your frequency of Q is 0.41. Okay? So in nature, populations are going to evolve. They are expected, it's expected in all populations most of the time because plants and animals, organisms are going to respond to their changing environment. Okay? Genetic drift changes allele frequencies due to chance alone. Okay? So genetic drift, here's your initial population. Genetic drift is after a bottleneck event, like a hurricane or whatever. Remember that. Okay, so this is going to throw you out of Hardy-Weinberg, right? So, but if we know Hardy-Weinberg, we're going to know if this happens. Gene flow is going to move alleles from one population to another. So this is our initial population. You can see that more green marbles arrive and orange marbles leave, and as a result, that's going to change the allele frequency. Mutations produce genetic variation. So here's our initial population again, but now we have a new allele that's red. This, if red happens to increase mating success, then you're going to have an increase in this new allele based on mating success. Sexual selection selects for traits that improve mating success. So if the blue alleles are associated with something that females like, then they like a blue body, then eventually over time, most of the animals are going to be blue just based on the fact that that's what females like to mate with. Natural selection, again, survival of the fittest. If the white alleles are determined to be the most fit, they blend into the background or something. Therefore, their frequency is going to increase because predators will not get them.